bonding jumper is required in a separately derived system. A separately derived system is an electrical power source, such as a generator, transformer, or converter, that is not directly connected to the main service. These systems create a new neutral point and require specific grounding and bonding practices to ensure electrical safety. The purpose of a bonding jumper is to connect the equipment grounding conductor to the grounded conductor, typically the neutral, at the source of the separately derived system. This connection establishes a low impedance path for fault current to return to the source, allowing overcurrent protection devices like circuit breakers or fuses to quickly clear the fault. Without a bonding jumper, a ground fault could create a dangerous voltage on metal parts of equipment, posing a shock hazard. The National Electrical Code (NEC) provides detailed requirements for grounding and bonding separately derived systems in Article 250. Specifically, Section 250.30 addresses the grounding of separately derived alternating current systems. The size of the bonding jumper is determined by NEC Table 250.102. C1, which relates the size of the ungrounded conductors to the required size of the bonding jumper. It's essential to consult this table to ensure the bonding jumper is appropriately sized to handle potential fault currents. Proper installation of the bonding jumper is crucial. It should be securely connected to both the equipment grounding bus and the neutral bus at the source of the separately derived system. The connection should be made using listed connectors and according to manufacturer's instructions. The bonding jumper must be made of copper or another corrosion-resistant material and should be protected from physical damage. In some cases, a grounding electrode conductor (GEC) is also required for separately derived systems. The GEC connects the grounding bus to a grounding electrode, such as a ground rod, ground ring, or a metal water pipe. The purpose of the GEC is to provide a path to earth for dissipating stray currents and stabilizing the system voltage with respect to ground. The size of the GEC is determined by NEC Table 250.66 based on the size of the ungrounded conductors. It's important to note that the requirements for grounding and bonding separately derived systems can vary depending on the specific type of system and the voltage levels involved. For example, systems operating at less than 50 volts may have different requirements than systems operating at higher voltages. Similarly, systems that supply critical loads, such as emergency lighting or fire pumps, may have additional requirements. In addition to the NEC, local codes and regulations may also apply to the installation of separately derived systems. It's essential to consult with a qualified electrical inspector or engineer to ensure compliance with all applicable requirements. Common mistakes to avoid when installing bonding jumpers: firstly, failing to properly size the bonding jumper according to NEC Table 250.102. C1. Secondly, using undersized or unapproved connectors. Thirdly, neglecting to securely connect the bonding jumper to both the equipment grounding bus and the neutral bus. Fourthly, failing to protect the bonding jumper from physical damage. Fifthly, not considering the requirements for grounding electrode conductors in addition to the bonding jumper. Sixthly, ignoring local codes and regulations that may apply to separately derived systems. Understanding the principles of grounding and bonding is essential for ensuring electrical safety in separately derived systems. Proper installation of bonding jumpers and grounding electrode conductors helps to minimize the risk of electric shock, fire, and equipment damage. Consulting with qualified professionals and adhering to the NEC and local codes are crucial for safe and compliant installations. Here are some specific examples of how bonding jumpers are used in different types of separately derived systems. Firstly, in generators, the bonding jumper connects the generator frame to the neutral terminal, ensuring that the generator is properly grounded. Secondly, in transformers, the bonding jumper connects the transformer case to the neutral point of the secondary winding, providing a low impedance path for fault current. Thirdly, in solar photovoltaic systems, the bonding jumper connects the inverter chassis to the grounding electrode system, protecting against ground faults. In each of these cases, the bonding jumper plays a critical role in maintaining electrical safety and preventing equipment damage. Proper installation and maintenance of bonding jumpers are essential for the safe and reliable operation of separately derived systems. Here is some additional information about bonding jumpers. Bonding jumpers are typically made of copper or aluminum, although other conductive materials may be used in certain applications. The size of the bonding jumper is determined by the available fault current and the clearing time of the overcurrent protection device. A larger bonding jumper is required for systems with higher fault currents or longer clearing times. The bonding jumper should be installed in a manner that minimizes its length and impedance. Sharp bends or kinks in the bonding jumper can increase its impedance and reduce its effectiveness. The bonding jumper should be protected from corrosion and physical damage. Corrosion can increase the impedance of the bonding jumper and reduce its ability to carry fault current. Physical damage can break or disconnect the bonding jumper, rendering it ineffective. Regular inspection and maintenance of bonding jumpers are essential for ensuring their continued effectiveness. Bonding jumpers should be inspected for corrosion, damage, and loose connections. Any problems should be corrected immediately to prevent electrical hazards. In addition to bonding jumpers, other grounding and bonding measures may be required for separately derived systems. These measures may include the use of grounding electrodes, equipment grounding conductors, and ground fault protection devices. The specific requirements will depend on the type of system, the voltage levels involved, and the applicable codes and regulations. It's important to consult with a qualified electrical professional to determine the appropriate grounding and bonding measures for each specific application. Bonding jumpers play a critical role in electrical safety by providing a low impedance path for fault current to return to the source. This allows overcurrent protection devices to quickly clear the fault, minimizing the risk of electric shock, fire, and equipment damage. Proper installation and maintenance of bonding jumpers are essential for the safe and reliable operation of electrical systems. It's also important to understand the difference between bonding and grounding. Grounding refers to connecting an electrical system to the earth, typically through a grounding electrode. Bonding refers to connecting different metal parts of an electrical system together to create a low impedance path for fault current. Both grounding and bonding are essential for electrical safety, but they serve different purposes. Grounding helps to stabilize the system voltage with respect to earth and provides a path for dissipating stray currents. Bonding helps to minimize the voltage difference between different metal parts of the system, reducing the risk of electric shock. In summary, a bonding jumper is a critical component of a separately derived system, ensuring a safe and effective path for fault currents. Always consult the NEC and local codes for specific requirements and best practices when installing and maintaining these systems.